Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper trending on X, published on July 8th, 2025, just 2 days ago. This paper shows something pretty counterintuitive, that you can match the performance of a state-of-the-art post-training recipe without using any data from powerful models like GPT-4o. The paper is titled, "The Delta Learning Hypothesis: Preference Tuning on Weak Data Can Yield Strong Gains," and the implications for model training are quite significant. The authors propose the delta learning hypothesis, which suggests a model can improve simply by learning to prefer one weak response over an even weaker one. This first figure really visualizes that core idea. On the left, we have training data from two models, a Llama 3 3B and an even weaker Llama 3 1B. Both are less capable than the student model, Tulu 3 8B. Now, if you use supervised fine-tuning, just showing the model the better weak data to copy, its performance drops. But if you use direct preference optimization, or DPO, a method that teaches the model to simply prefer one response over another, its performance actually goes up by over 5%. This result is quite remarkable. Building on what we saw, this next table quantifies the results from their pilot study. They tuned Llama 3 instruct models using a dataset called Ultra Feedback Weak, which was generated by models even weaker than Llama 3. Now, when they use direct preference optimization to teach the model to simply prefer a weak response over a weaker one, they see clear performance gains, shown in blue. But when they use supervised fine-tuning, where the model just copies those same weak responses, performance actually gets worse, which you can see highlighted in orange. To really put this to the test, the authors then ran more controlled experiments. This table details what happened when they applied these methods to two different Llama models. When they used supervised fine-tuning, a technique where the model just copies the better of two weak answers, performance drops across the board. You can see those scores in orange. But when they used direct preference optimization, just teaching the model to prefer that same answer over an even weaker one, the performance consistently improves, as shown in the blue rows. This pattern holds true for both models. Okay, so this diagram visualizes how they simplify a state-of-the-art training recipe. The top half shows the standard complicated method for Tulu 3. It uses a whole pool of strong models, like Llama 70B and GPT-4o, and then has GPT-4o act as a judge to pick the best response. Now, their simple recipe on the bottom is much different. It uses just two weak models and a simple rule, or heuristic. It assumes the slightly larger model's response is better. This simple preference pair is then used for direct preference optimization, completely cutting out the need for expensive, powerful models. Alright, so this next table really puts that simplified recipe to the test on a large scale. The baseline model, a Tulu 3 8B, starts with an average score of about 57% across several benchmarks. Now, the original Tulu 3 recipe, using that expensive GPT-4o data, gets the score up to 63%, which you can see in pink. But here's the amazing part. Their best simplified recipe, just using preference data from two much weaker QN models, actually scores 63.4%. This result shows their simple, cheap method matches the performance of the state-of-the-art recipe. This next plot provides a fantastic visual summary of why their simple recipe is so effective. The horizontal axis shows the quality of the chosen data, basically how good it is compared to the student model itself. The vertical axis shows the actual performance change after training. Now look at the red triangles for supervised fine-tuning. They only show gains when the data is much better. But the blue dots for direct preference optimization tell a different story. Even when the data is weaker than the student model, inside that green box, performance still increases significantly. So what's the big takeaway here? The central idea, which the authors call the delta learning hypothesis, is that a model doesn't need perfect data to improve. Instead, it can learn from the relative quality difference between two weak examples. By using direct preference optimization, which just teaches a model to prefer one response over another, they achieved results that matched expensive training methods that rely on much stronger models. This is a huge deal for making powerful model training more accessible. Thanks for tuning in to the AI Research Roundup. I'm your host, Alex.